Hey, this is Nathan Schmidt. So I was experimenting with Google's Gemini AI, and it did something interesting. It created a 5-minute audio report sort of discussion on the tricorder framework. So if you don't feel like listening to my 2.5 hour rant on the tricorder framework, this video might be for you. So enjoy.
Welcome to the deep dive. Today, we're really plunging into something pretty fascinating. It's called the tricorder framework.
Yes, developed by Nathan O. Schmidt. And what's really striking is its origin it comes straight out of theoretical physics.
Right, trying to solve some really big foundational problems.
Exactly.
Good.
Deep mysteries of the universe kind of problems.
So our mission for you, listening in, is to sort of unpack this. How does it unify coordinate systems? And what's this about circles becoming active separators?
With intrinsic directional properties. And there's also a really interesting computational efficiency angle we should touch on.
Definitely. Okay, let's start with the person behind it, Nathan O. Schmidt. What's his background?
Well, he has quite a unique mix. Master's degrees in both computer science and mathematics.
Ah, okay, so he's got the computational and the theoretical chops.
Precisely. And he's affiliated with the Cold Hammer R&D. The framework itself is very new, a preprint from June 2025.
So super current. And you said it came from specific physics problems. He wasn't just playing with abstract math.
No, not at all. The motivation was very concrete, well, as concrete as theoretical physics gets. Things like quark confinement.
How quarks get stuck together inside particles.
Right. And also the physics around black holes. He even used a concept called time zone T in his quark work, which is sort of analogous to the boundary circle in this framework.
Interesting, like defining a containment zone.
Exactly that. An abstract mathematical boundary applied to, fundamental particle physics.
Okay, so that leads to the core question. What does this tricorder framework actually do? What's the main innovation here?
Fundamentally, it's a generalized coordinate system. Think of it as a way to get complex, Cartesian, and polar coordinates playing nicely together on the complex plane, all unified.
How does it manage that?
It rests on two key theorems, foundational ideas.
Okay.
Lay them up on us. First is the tricorder topological duality theorem. This is where circles, often just called TR or T, get redefined. They're not just static lines. They become active separators, dynamic, with intrinsic directional properties.
So they have a direction built in, like a little compass on the circle itself.
Sort of, yes.
Yeah.
It establishes this duality, a connection between the zone inside the circle, XR, and the zone outside, X plus R. And he uses something called phase pair mapping to link them.
Phase pairs.
Oh.
Okay, what does that mapping do?
It ensures that the essential relationships between points are preserved,
Yeah.
even as things conceptually move across this active boundary. It's clever.
So circles are now dynamic borders that actively manage what's inside versus outside. That is a different way of thinking. What's the second theorem?
That's the Escher tricorder reflective duality theorem. This one brings in reflective duality across the boundary.
Reflective, like a mirror.
Exactly like a mirror. Uses a circle inversion map. Think of it flipping the inside zone to the outside and the outside to the inside.
Okay.
But crucially, it does this while preserving those phase pair relationships we just mentioned. It keeps everything consistent during the flip.
That sounds elegant. And you mentioned a trichotomy-defined structured orientation.
Right, that's another layer. It basically assigns specific directional properties to points based on their angle. Adds more precision.
Makes sense. Which actually brings me to the name tricorder. Why that specific name? It sounds a bit like a fraction.
Good question. It's not really fractional. The tri part refers to unifying those three coordinate systems complex, Cartesian, polar, and also that trichotomy orientation thing.
Ah, okay. Three systems plus the trichotomy.
Yes, and the quarter part refers to how it partitions the plane. You have the inner zone, the outer zone, and the boundary itself. Kind of like quadrants, but defined by the circle.
Got it. So tri for the three systems and the orientation, quarter for the zones. Much richer than it sounds. Okay, clearly powerful stuff for theoretical physics. But let's talk practicalities. Does this have legs outside the lab? Can it, help us build faster computers or something?
Actually, yes. There's a really significant measurable benefit in computational efficiency.
Oh, tell me more.
In one case study, they demonstrated the framework was used to reduce the maximum number of comparison checks needed in a certain type of algorithm.
Okay.
It went from 7 checks down to just 4.
Wait, 7 down to 4. That's nearly cutting it in half.
It's a substantial reduction, yeah. For certain computational problems, that kind of optimization is a really big deal. Direct speed up.
Wow. Okay, so that's a concrete win. Where else could this apply? What's the bigger picture?
Well, thinking more broadly, you could see applications in signal processing, maybe for more efficient filtering, in engineering, perhaps computational fluid dynamics or advanced graphics rendering.
Things with complex boundaries or symmetries?
Exactly. Anywhere circular symmetry or precise boundary handling matters, even potentially in areas like quantum computing, algorithm design.
Yeah.
Applied sciences could really benefit.
So wrapping this up then, the tricorder framework. It's this deep mathematical idea from Nathan Schmidt, born from physics challenges like quark confinement.
Very abstract origins.
But it actually leads to tangible benefits, like potentially faster computations, and could impact engineering, signal processing, a whole range of fields.
It really bridges that gap between the purely theoretical and the practical, measurable world.
It's quite something.
And it makes you wonder, doesn't it? How often do these incredibly abstract ideas, cooked up to solve really esoteric problems, end up having these unexpected, profound impacts on technology we might use every day? Something for you to think about.
Definitely food for thought. So after this deep dive, what stands out most to you?